This is a simulation of the universe using a picture of the Hubble Deep Field. And what I want to show you here is that you can shrink the universe or expand the universe, and proportionally distances within it will not change. So you could shrink all the way, say, back to a black hole, and the dimensions would still be the same. The meter stick would still be the same, and the clock rate has to slow down proportionally also. Otherwise, things won't be the same. As you can see, they must be. So this is showing an outside dimension, which is colored in yellow. And we know that dimension must exist. Why must it exist? Because otherwise, if the universe were to expand or shrink due to cosmic expansion, and this is what we call it, there would be nothing for it to be expanding relative to. So this coordinate system, this larger coordinate system, must exist. And this is what I'll be calling the fourth dimension, or the ethereal dimension. So I just want you to see that. Now, everything that is not mass, and that includes light, is going to be transmitted outside the physical dimension, because light, okay, this is important. And this accounts for the experiments that showed over 100 years ago that the closer you get to the Earth, the more a meter stick will shrink and clock speed will diminish at the same time. And the reason for that? What you're looking at in that scenario is cosmic expansion. Unfortunately, they took the data from those experiments and used that to validate Einstein's theory of relativity, and it doesn't make any sense whatsoever. All that makes sense, and all you want to know or need to know, is that length and distance shrink or expand along with cosmic expansion. So from the inside, you won't be able to see this happen or experience it happen. So in this last illustration, we were showing how light shifts towards the red as it's leaving a source of gravitation. Even if there's no change in distance between source and observer, the light is going to change from blue to red. Or if the beam of light is aimed away from Earth towards the Earth will receive it shifting towards blue. That's what they call gravitational redshift. The main thing to take notice of here is the distance between the two objects doesn't change. And the same thing is true of cosmic expansion, and we showed how that works. Everything expands. Nothing inside has any idea that anything has changed. And that would apply all the way to the black hole if we're just talking about cosmic expansion here. So in this illustration, we're talking about another kind of redshift called Doppler redshift. It was explained by a man by the name of Doppler. And the fellow on the upper side, in that illustration, the object is moving away. The source of light is moving away from him. And what that means is that the light will be stretched out towards the red. It's just like a train when it goes by and the whistle goes zzz, all right? And then if the train is coming towards you, like what would happen with the guy on the blue, it goes to so anyway, and if the train is just sitting still, of course, it's going to be somewhere in between. So this is a Doppler redshift in light. And now, oddly enough, I got this off a physics webpage that is using it to explain why the cosmos is expanding. And they interpolate this all the way back to the Big Bang. They say the distances were less back then, and now they're bigger and bigger. But guess what? We just saw for ourselves, including some of what Einstein did, that distances don't change because the yardsticks and the clocks will expand or contract along with the expansion of the cosmos. So they're calling this a recessional velocity when there would be no recessional velocity due to cosmic expansion. So that's you know, major fault with the standard model. And that's why we're doing this. We want you to understand this. But I will say this, that we said that the universe was expanding with cosmic expansion in the first illustration. We just couldn't measure. But we know that there's an outside to that that transmits light, and in that massless dimension, it's very evident that gravitational redshift doesn't really exist. But in the fourth dimension, everything is receding away from every point in space is receding at the same time. And so everything is measuring redshifts of relative to each other, relative to the speed that they're moving apart. But we don't see that. We don't see the expansion anyway, but the Doppler shift in the fourth dimension is reflected back to Earth when we receive it. And when we receive it, we see that, oh yeah, it looks like things are flying apart. But they're not in this dimension, understand? So what we're really looking at is with distant galaxies or quasars or suns, black holes or whatever they are, we're seeing a massive, maybe a little bit of a redshift. How strong a redshift we see depends on the difference in mass between the two objects. We're looking at a gravitational potential, just like we did on Earth. And we could match a falling body, the rate it's traveling to the shift of the spectrum towards the red due to Doppler shift, even though it's gravitation. But it is Doppler shift in a fourth dimension. So what we're saying here, what we're knowing here, is that all gravity is cosmic expansion. The universe as a whole, of course, is expanding in proportion to all of the mass it contains, whereas the space around the Earth is expanding at a rate much greater than us, but much, much less than the cosmos. And the redshift that we see is directly proportional to the rate of expansion or recessional velocity in the fourth dimension, or the velocity of a falling object in the physical dimension. Now, all of this stuff is critical to understanding the cosmic expansion model, which is the correct model. This is what's really going on. This is not to say that the physicists aren't right, that celestial objects are receding from each other, but that isn't the cause of the redshift, or at least it isn't a very significant part of the redshift. And apparently they're trying to correlate this celestial recession with the redshift data that they get and use that to come up with distances when they're two entirely different things. If the universe really has been expanding all that time, then the value of g, the universal gravitational constant, would have changed, because the concentration of mass, even though it would measure the same in this dimension, it's not the same, and it's diminished a great deal since then. So that would cause the celestial objects to recede from each other as well, but that would be a secondary after the fact sort of expansion. And we just want to make this clear, that the cosmic expansion they're measuring is actually recessional velocity in the physical dimension. It is not cosmic expansion, and this should get them an F on any physics exam. And yet, apparently, you either believe this or you find yourself another job if you're a physicist. And this is what we're bucking here, okay? Good for now.